Welcome to this virtualized Industrial Strategy Challenge Fund Digital Security by Design, looking at technology-enabled business-led demonstrator in this Stage 1 workshop. Today I want to tell you about CHERI, which is fundamental to this challenge. CHERI is some research that's been undertaken at Cambridge and SRI International to look at how do we fundamentally improve computer security, including both hardware and software. This work has been undertaken over 9 years so far, with over 140 researcher years of effort, primarily funded by DARPA in the US. Much of the work has been led out of Cambridge. I'm Simon Moore, the person on the left. The lead security and architect of this work is Robert Watson, and Peter Sewell has led the verification effort on this project. So let me introduce this talk today. I'm going to give you a background to the CHERI architecture model that underpins the ARM Morello board, and we're going to look at how software works with this hardware architecture. There's lots of other things that you can read about. There's an introductory guide to CHERI, and there's also a much longer technical report that goes into great level of detail about the CHERI instruction set architecture. Let's motivate the work, and in particular talk about memory safety. So Ian Levy at NCSE is quoted as saying that buffer overflows have not objectively gone down in the last 40 years, and yet the impact of buffer overflows on security has, if anything, gone up. This is crazy. Why are we still seeing the same problems over and over again? Well, now with CHERI, we can really have hardware and software that gets to the heart of this problem. Similarly, Matt Miller at the Microsoft Response Center has analysed their vulnerabilities, and over 70% of vulnerabilities over the last 12 years are memory safety bugs. And in first place is spatial memory safety. And CHERI very directly addresses this. If you simply recompile software, you get a huge amount of spatial memory safety. And in second place are use after free type bugs. And we've got ongoing work that demonstrates that CHERI is very effective at mitigating use after free vulnerabilities. Let's now talk about the CHERI architecture. We've refined the architecture over a 9-year period, beginning with very simple models on risk processors, looking at particularly at sort of bounds check, then moving into compartmentalization, and looking at how C and C++ can make use of these facilities. We've done lots of optimizations on the capability format and how coding is done efficiently. We've done a lot of work on how this CHERI security model works with the operating system kernel, and more recently, temporal memory safety. CHERI aims to uphold a couple of really important principles. The first one is the principle of intentional use. We want to ensure that software runs the way the programmer intended, not the way the attacker tricked it. So, for example, we want guaranteed pointer integrity and provenance with efficient dynamic bounds checking. We also want to uphold the principle of least privilege, which is an idea really dating back a long way in computer security, but it's very hard to implement on current hardware. Using the principle of least privilege, we can reduce the attack surface using software-based compartmentalization with hardware support. And this mitigates both known and unknown vulnerability exploit classes, which is very powerful. And our approach is highly scalable and highly efficient compartmentalization. Let's talk about the CHERI architectural additions. So CHERI adds a new type called the capability. And a capability is a bounds checked pointer with integrity and provenance properties. It's held in memory and also in new or extended registers. So if we begin with a 64-bit address, to that we add permissions, we add bounds of top and bottom region, and which we compress, and also there is a sealed bit which I won't dig into today. That brings us up to 128 bits. We then add a hidden validity tag that is absolutely critical for security, that guarantees the integrity and provenance of pointers. As depicted here, the compressed bounds point to a region of memory, and the address must be within those bounds if you dereference that address. In other words, if you access memory. We do actually allow the address to stray a little outside these bounds during address calculations, basically to retain backwards compatibility with C and C++ code and others. We also add new instructions. So we have new instructions to undertake loads and stores via these bound checked capabilities, and we get an exception if the address is out of range. The instruction set also guarantees guarded manipulation of capabilities. So for example, you can only decrease the bounds and decrease permissions. You can adjust the address, extract and test fields, and also we have what's called constrained non-monotonic domain transition instructions for compartmentalization. The decrease in bounds and decrease in permissions are an example of an important security property. So we get this monotonic decrease in these writes, and we verify these using formal methods since they're absolutely critical security properties. CHERI is a portable protection model. Our early research was actually on a MIPS-based architecture to which we added CHERI extensions. But very much like virtual memory, the CHERI protection model can be portable while its actual integration into the instruction set can be specific to that instruction set. So for example, on current machines that support virtual memory, they will have different page table formats, and they may use a hardware-based table walker or software-based table walker and so on. It doesn't matter about the very specific low-level bits of the implementation because the abstract model is the same. So for applications, you get virtual memory, and we know what that means. Similarly for CHERI. Our current research is on an open source RISC-V based system. And of course, we're very excited by ARM, who've been working with us for the last 5 years to look at extending the ARM V8 model to support CHERI. And under this program, that results in the Morello prototype that explores this space. We've also looked at x86, but really only in a draft form. For all of these portable models, we're also looking at guaranteeing key security properties and to which we verify. And you can read about all of these in our CHERI ISA V7 technical report, and of course ARM's forthcoming Morello specification. Let me now tell you about the CHERI C and C++ memory protection model. So we're going to talk about applying capabilities to all integer addresses throughout the address space. So that includes all data pointers, but also all code pointers, so things like return addresses and so on. Bounds and permissions are minimized by the software, so including the kernel, the runtime linker, the memory allocator, and of course compiler generated code. And the hardware permits fetch, load, store only through these granted capabilities. And the tags on those capabilities ensure integrity and provenance of all of those pointers. So the memory protection for the language and the runtime are refined by the kernel, the runtime linker, the compiler generated code, and the heap allocator. The protection mechanisms provide spatial memory safety and privilege minimization. So they also support temporal and memory safety. So, for example, mitigating use after free type bugs, and referential memory safety. Can be applied at two levels. So we have the language level pointers that point explicitly at the stack and heap allocations and global variables. And then there are the sub-language pointers used to implement control flow, linkage, and so on. The sub-language protection mitigates bugs in the language runtime and generated code, as well as attacks that cannot be mitigated by high-level memory safety. Let me tell you a little bit about our operating system work. So we've got a complete memory and pointer safe version of FreeBSD, so a substantial Unix-style operating system that includes, of course, C and C++ in the kernel, plus user space. So the operating system, of course, includes all the usual things: file systems, networking, device drivers. We also support pure capability libraries and system tools. And then on top of that, we can run applications like Postgres database, Nginx for web use, WebKit, and so on. Valid provenance, minimized privilege for pointers are all with regard to virtual addresses. The user space capabilities originate in kernel provided routes, and the compiler allocators, runtime linker, and so on refine the bounds and permissions to narrow them as appropriate. We trade off privilege minimization, monotonicity, and API conformance. So typically, memory management, we basically modify, realloc, mmap, mprotect, and so on. We've done a lot of work on the operating system interface, including this award-winning paper on the CHERI ABI. So let me give you an example of a past vulnerability where we really make inroads using this software model on top of our CHERI hardware. So the Google Project Zero released and analyzed a set of zero-day exploits against the Apple's iOS. Current CHERI mitigations address all of the exploit chains at the first stage, even without temporal safety. But every chain relies on heap aliasing, so temporal vulnerability, as an intermediate step for the kernel control. And the chain 5 in this exploit step suggests that CHERI-aware exploits taking advantage of temporal memory safety vulnerabilities might be possible. We're undertaking further work looking at WebKit, JavaScript, and so on to analyse how we mitigate vulnerabilities in those systems. Let me now tell you about CHERI-based compartmentalisation. Here we want to apply the notion of application level least privilege. So software compartmentalisation decomposes software into isolated components with delegated limited rights. The potential compartmentalisation boundaries tend to match reasonable user expectations for least privilege that can be found in many user-facing applications. So for example, if we've got an email client, then of course the client will run in a process using conventional process-based protection techniques, but then within that application we want to further compartmentalize things. So for example, every email account you'll want to run in a separate compartment. Every message that you'll want to run in a compartment, and if you have an attachment, you'd also want that to be held within a compartment, and if it's opened up, then it gets opened up also in a separate compartment. And this really mitigates, malicious emails, malicious content that's been attached. Using this technique, we're able to mitigate not only unknown vulnerabilities, but also as yet undiscovered classes of vulnerability. This form of compartmentalization is just incredibly powerful. So how is it done? CHERI-based compartmentalization, basically we have to look at the set of capabilities that applications have. So we want to isolate compartments, effectively using graphs of capabilities combined with constrained non-monotonic domain transitions to move between these isolated regions. So for instance, we've got protection domain A, that's got a set of capabilities, and you can look at the reachability graph of that set of capabilities. We can then have another protection domain B, and we can have an overlapping region if necessary to share resources efficiently. So there are all sorts of proposed models of compartmentalization. So one approach is to isolate dynamically linked libraries. Another one is to adopt something rather like the Unix coprocess model, but actually use CHERI-based protections instead, which turned out to be much more efficient. We still have ongoing research to be done in that space over the next year or two. We have undertaken some micro-benchmarking on this, and here are some early results. So here we're just looking at moving data between two compartments, and on the x-axis we've got the payload of the amount of data. You'll notice it's logarithmic in the x-axis. It's also logarithmic in the y-axis for the number of processor cycles when we're running the processor on FPGA. So you'll notice that when we've got a small amount of data we're moving, under a kilobyte, which is then for the coprocess model on top of CHERI, that's the blue line. And if we then compare that against simple process-based protection, so we're running basically the two protection domains as almost different applications with a Unix pipe between them, then we're 2 orders of magnitude more efficient. And even by the time we're moving large quantities of data, we're still very significantly efficient. This is very important because it means that we can basically do compartmentalization with not much more cost than doing a function call. And that really is quite critical to applying compartmentalization at many different scales. So lots of opportunities and challenges. So CHERI dramatically improves compartmentalization scalability. We can have more compartments, we can have more frequent domain transitions, and we can have faster shared memory between compartments. There are lots of use cases. So we could sandbox all sorts of different things and at different levels. And unlike memory protection, software compartmentalization also requires careful software refactoring to support strong encapsulation, and it affects the software operational model. So we do need work to do tooling and to develop techniques in this space. Let me tell you about the software stack that we have so far that's been funded by DARPA. So we're building all of this on top of our DARPA-funded research. So over the next 3 to 4 years, we're going to push our stable platform out through ARM and Linaro, and Cambridge and Edinburgh will refine the model and verify key properties. We have other consortium partners, including Google and Microsoft, and we're waiting to see how the EPSRC-funded academic community appears. We're quite excited about that, getting more people involved We expect to see innovative funded industrial R&D. We're also hoping to engage with people in the US. We've had quite a bit of engagement through our DARPA funding, and we hope to see if DARPA can also fund some of the work in the US. The target use cases include the Morello evaluation platform, the Morello Demonstrator prototyping, and also further CHERI hardware and software research and development that is open source. We've got various demonstrations of working CHERI software. So we've got very good compiler support that's for fine-grained C and C++ language memory protection. So if you just recompile code, then you get a huge amount of protection against buffer overflows, buffer overreads, pointer corruption, injection faults, and so on. And in fact, the main impediment we find to recompiling code is simply removing the bugs. We do tend to find there are bugs in there where some of them that might be malign, but some of them may be vulnerabilities, and clearly things that one wants to fix. We also, of course, want to push on scalable, efficient compartmentalization to improve the performance, scalability, and programmability of fine-grained software isolation and communication to enable new software design patterns resisting a variety of adversary models. So the software protection stack on Morello is fairly layered. At Cambridge, we've done work on open source applications. Our work is very much focused on FreeBSD variant, i.e. the CHERI BSD that we have available for Morello, will have available for Morello, and also for our CHERI RISC-V platform. Lenaro will focus much more on Android. We'll work with Google with a Hafnium supervisor, because we want to really exploit CHERI-based compartmentalization for Hafnium. And finally, the bottom of this is our compiler toolchain suite, which is increasingly mature. And we're really focused on incremental rather than clean slate CHERI deployment. We've done a lot of work, and things are in a very good state. So let's conclude. CHERI enables new software models through hardware support for fine-grained memory protection and scalable software compartmentalization. It's developed over 10 years through DARPA-supported research into both the hardware and the software. And ARM has been working with us for 5 years. That's led up to the Morello prototype platform, so system on chip, board, and the associated software for it. Really excited about that, and that's a good segue into the next talk. The open source DARPA-funded CHERI software stack is already available in open repositories, and we have links to that and documentation. And there's further research and development activities over the next few years. We'd like to thank other sponsors, so including not only DARPA, but ARM, Google, EPSRC, and so on. And finally, an invitation to collaborate. It is an exciting moment for CHERI, and we are really excited to be able to engage with people, talking about industrial collaboration, looking at different application domains, seeing how the technology can be deployed, working with ARM and others to mature the software baseline, working on the formal foundations. We encourage people to engage on the formal method side, and there are lots of opportunities to grow the research community. There's URL there and some pointers to overview documents of the underlying technology. Thank you very much.